Welcome to ScienceCover.com. In this session, we will look at refraction. We'll explore what we mean by refraction, investigate the refraction experiment, explain why refraction happens, and look at lenses. Before we begin, pause the video and complete the Do Now task. Let's check our answers. Number 1. A reflection can be seen on the surface of a glass object. What does this tell us about the glass object? It means that on a microscopic level, the surface must be flat. Question 2. No reflection can be seen on a wooden table surface. What does this tell us about the table surface? This means that on a microscopic level, this surface is uneven. Question 3. What is the normal? This is an imaginary line perpendicular to the surface at the point where a wave moves from one medium into another. Question 4. What is the name of the angle between the normal and the incoming ray? This is the angle of incidence. What is the name of the angle between the normal and the outgoing ray? This is the angle of reflection. What is the rule of reflection? That is that the angle of incidence must be equal to the angle of reflection. Now let's look at refraction. Let's first understand what we mean when we speak about refraction. Refraction is a change in direction of light caused when it moves from one medium into another. The light reflected off this pen speeds up as it moves from water into the air. This causes the light to change direction. The pen now appears larger under the water and appears although it's lying in a different position. Glasses work as the light travels fast in the air, but slows down when it enters the glass. This changes the direction of the light, allowing it to be focused on the retina. When the sun is low in the sky, it loses its circular shape and becomes oval. This is an effect of refraction. Light from the bottom of the sun is traveling through more atmosphere to get to your eye than the light from the top of the sun. This causes the sun to appear shorter. In this example, a man has gone spearfishing. If the man throws a spear in a straight line at the fish, he will hit nothing but water. The location of the fish is much closer to the man, as shown by the red line. This is because refraction changes the direction of the light leaving the water as it enters the air. Pause the video now and complete task 1. Let's check our answers. Number 1. What is refraction? This is the change in direction of a wave or light as it moves from one medium into another. Number 2. What causes refraction? This is a change in speed of the waves as it moves faster in one medium than the other. Question 3. Give two examples of refraction in the world around us. These could be objects appearing at different locations when viewed through water, the sun appearing oval as it approaches the horizon, or water waves bending as they approach the shore. Any other sensible suggestion is also acceptable. Which location should this man throw his spear? The answer should be A. This is because the light leaving the water will increase in speed. It will bend away from the normal, and this causes the light to refract. The fish will appear at position B, but actually be closer to the fisherman. And A is the point that is closer to the fisherman than B. Now let's look at the refraction experiment. In this experiment, a ray of light is shone into a glass block. Upon entering the block, the ray of light slows down. This causes the light to bend towards the normal. Upon leaving the block, the ray of light speeds up. This causes the light to bend away from the normal. The wavelength of the light entering the block and leaving the block is the same. However, when the light enters the block, it travels slower, meaning that the waves are closer together within the block. This means that the light inside the block has a lower wavelength than the light traveling in the air. This animation shows a close-up of what is happening to the wave at a boundary. We can see our ray coming from the left-hand side and striking the glass block. As it does so, the wave slows down and the wavelengths bunch closer together. When light enters a triangular prism, the light slows and bends towards the normal. On leaving the prism, the light speeds up and bends away from the normal. White light contains all of the colors of the spectrum. Different wavelengths of light refract by different amounts. So blue, for instance, reflects slightly more than red light. So if we place white light into a prism, the red and blue light take a separate path. When they leave the prism, they'll be traveling in slightly different directions. This is true for all of the different colors of light. And this is how a spectrum is created. Pause the video now and complete task 2. Let's check our answers. In part A, we had to show the path of light takes within the block. This is marked between the two normals, as shown in the diagram. The wavelengths of the rays inside the block should have been shorter than the wavelengths of the rays outside the block. And our explanation is that the ray of light travels slower within the glass than in the air. This means that the ray slows down when it hits the block. As the left-hand side of the ray enters the block first, this side slows down first. This causes a change in direction and bends the light towards the normal. A student shines a ray of red light into a triangular prism. Add a line to show the path of the red light through the prism. This should bend towards the normal on entering the glass and bend away from the normal on leaving the glass, as shown in the diagram. The student replaces the red light with white light. Explain what the student will observe and why. The student should now see a spectrum, and this is created as the white light is made up of many different colors or wavelengths of light. The different colors or wavelengths will refract at different angles as they pass through the prism. Now we will look at how to explain refraction. We know that light travels at different speeds in different materials. As light moves from air into glass, the light will travel quickly in the air and then slow down as it enters the glass, and this causes a change in direction of the light. To explain why this happens, we can compare it to a car traveling from a road surface onto a sand surface at an angle. As the car moves from one surface to the other, the first tyre that will leave the road surface and hit the sand surface is the car's front right tyre. This means that if we look at the two front wheels of the car, the left-hand wheel is travelling quickly, whereas the right-hand wheel has been slowed by the friction of the sand. This causes a turn in motion on the car, which will change the direction in which it's travelling. Pause the video now and complete task 3. Let's check our answers. The missing labels on the diagram: the front left wheel is travelling quickly, the front right wheel is slowed by friction, and the friction causes a change in direction. Explain how the student can use this analogy to help describe the effects of refraction. As the car leaves the road onto the sand, the resistance to its motion increases. This can be compared with the change in motion of waves as they move from one medium into another. As the front right wheel of the car hits the sand first, this wheel slows, causing the car to bend towards the normal. This can be compared with how waves will slow on entering denser materials and bend towards the normal. Now let us look at how we use refraction in lenses. Refraction can be used by lenses to change the direction of light. There are two types of lens: convex or converging, and concave or diverging. A convex lens is wider at the center. This causes the parallel rays to converge to a point. We call this point the focal point. A concave lens is wider at the edges than at the center. This causes the parallel rays to diverge and move out from the center. Some books represent convex lenses as a line with outward pointing arrows, and a concave lens as a line with inward pointing arrows. If the parallel rays are entering the lens at an angle, then the position of the focal point changes. The new focal point can be found by continuing the path of the central line. The new focal point will be found directly below the original focal point, however along this central line. And so we can bend the other parallel rays so that they cross at this location. A lens can be used to produce an image. This arrow represents the height of an object. There are three rays of light coming from the top of this object. One shows the path of light travelling through the top of the lens, one shows the path of light travelling through the centre of the lens, and the third ray of light travels through a point of focal length away from the lens. Any light travelling through the centre of the lens will continue in a straight line. This light is not refracted. But the light travelling through the point marked a focal length away from the lens, this will become horizontal. The third ray will bend down to meet the other two rays where they cross. This will be the location where an image is formed. Pause the video and complete task 4. Let's check our answers. Question 1a. The three rays of light will all bend and converge at a focal point. In 1b, the three rays of light will diverge and move out from the centre of the lens. In 1c, the three rays of light will converge to a point below the focal point on the principal axis. In D, we can see that the three rays of light will converge to a point where they form an image.